All right, everyone, welcome to the main event. Tonight, we are stepping into the ring for a massive elemental showdown. In this corner, weighing in with luster and strength, we have the mighty metals. And in the other corner, the challenger, we have the versatile and varied non-metals. Let's get ready to rumble.
So let's just stop and think about this for a second. What's really the difference between that roll of aluminum foil you use for your lunch and the actual oxygen that you're breathing right now to stay alive? I mean, they're both elements, right? But they play by a completely different set of rules. Today, we're going to figure out exactly what those rules are.
And ding, ding, ding! There's the bell for round one. We are kicking things off with the most obvious test, the physical properties showdown. This is all about what you can see and touch. How do metals look? How do they feel? How do they really stack up against the non-metals? Let's take a look.
You know, metals come to this fight with a pretty awesome set of tools. First up, they've got luster. That's just a fancy word for being super shiny. Most non-metals? Kind of dull. Metals are also malleable, which means you can hammer them into thin sheets without them breaking. Non-metals, on the other hand, are usually brittle. You hit them, they shatter. Then there's ductile, which means you can stretch them into long, thin wires. And they're sonorous. You hit one, and you get that classic, satisfying ring. And yeah, most of them are pretty hard and strong.
But wait, there's more. Their skills don't stop there. Metals are also amazing conductors. They let heat and electricity flow right through them, which is exactly why your pots and pans are made of metal. And nonmetals? They're usually the opposite. They're insulators. That's why the handle on that pot is probably made of plastic or wood to stop you from burning your hand.
So it all seems pretty simple, doesn't it? If it's shiny, strong, and conducts electricity, it's a metal. If it's dull and brittle, it's a nonmetal. Case closed. Well, not so fast. In the world of elements, for just about every rule, there's an exception. So let's meet some of these troublemakers.
Okay, so here's a big rule we all learn in school. Metals are solid at room temperature, right? You think of things like iron, copper, gold, they're all solid. It seems like a pretty safe bet, a real defining feature of being a metal. But is it really?
Nope, not even close. And this is where things get really interesting. For that whole all metals are solid rule, I'd like you to meet mercury, the only metal that's a liquid at room temperature. And what about the metals are hard rule? Well, alkali metals like sodium are actually so soft you can literally cut them with a butter knife. And the nonmetals are getting in on this rule-breaking action too. We think of them as dull, but check out iodine. It's a nonmetal, and it's actually pretty shiny.
And maybe the biggest plot twist of all involves carbon. As a nonmetal, it really shouldn't conduct electricity. But one of its forms, graphite, yeah, the same stuff that's in your pencil lead, is actually a decent conductor. This just proves you really can't judge an element by its cover.
This brings us to a huge question. If all these physical properties can be so misleading, how can we really tell the difference? What's the one true test that separates the champions from the contenders for good?
And that, my friends, brings us to round two, the ultimate chemical test. Forget about looks. This round is all about action. We're going to see what these elements are really made of based on how they behave and, more importantly, how they react. This is where we find their true character.
And you know, one of the best ways to test a metal's true personality is to see how it handles a little face-off with good old H2O. A metal's reaction with water tells you everything you need to know about its reactivity. It really separates the heavy hitters from the rest.
So we've broken down this challenge into 3 levels. First up, cold water. This is where you find the true drama queens of the periodic table, like sodium and potassium. They react so violently with cold water that they can literally burst into flames. Next, level 2, hot water. Metals like magnesium, they don't do much in cold water, but you turn up the heat and they'll start to react. And finally, for the really tough customers like iron and aluminum, you gotta bring in the final boss, steam.
And then you've got the totally unbothered crowd. Metals like lead, copper, silver, and gold. They are so unreactive, they just don't care. Cold water? Nope. Hot water? Not interested. Steam? They're just too cool for all that drama.
So after putting all our metals through these physical and chemical challenges, it is time to reveal the official power rankings. The results are in, the scores have been tallied, let's see who really came out on top.
Based on everything we've just seen, especially that intense water challenge, who do you think it is? Which metal earns the crown as the most reactive champion of them all?
And the champion is potassium. This right here is the official Reactivity Series, the ultimate leaderboard for metals. It's all arranged from the most reactive up at the top, down to the least reactive at the bottom.
And the rule is simple. Any metal can displace, or pretty much kick out, any metal below it on the list. That makes potassium the undisputed king, while gold, all the way down at the bottom, is perfectly happy just chilling out.
All right, we've covered a ton of ground, from physical looks to chemical showdowns. But before we wrap this up, let's see what you've learned. It's time for a quick bonus round. It's pop quiz time.
First question. We met this rebel early on. It's the one metal that completely shatters that all metals are solid rule. Can you name it?
That's right, it's mercury, the one and only liquid metal hanging out at room temperature, a true icon of the periodic table.
Okay, next question for you. We know from our reactivity list that sodium is way up there, near the top. It is so reactive that you have to store it in a really special way. Why is it kept under kerosene oil?
It is all about protection. Sodium is just so eager to react with things that if you leave it out in the open, it'll react violently with the oxygen and moisture in the air. It can even just catch fire all by itself. So the kerosene acts like a protective little blanket, keeping the air away and keeping that sodium nice and calm.
And for our final quiz question, let's go all the way back to round 1. We learned 2 key words that describe how metals can change their shape. So, what's the difference between being malleable and being ductile?
Here's the easiest way to remember it. Malleable means you can hammer it into thin sheets. Just think of aluminum foil. Ductile means you can pull it out into thin wires, like all the copper wires inside our electronics. So one's about sheets, the other is all about wires. Simple as that.
So what's the final takeaway from our big elemental showdown? Well, I think we've seen that when it comes to the elements, looks can be pretty deceiving. But chemical reactions, they don't lie. It's not just about how an element looks on the surface, it's about how it acts when the pressure's on that truly defines it. Thanks for tuning in.